Good morning or good afternoon, depending on where you're calling from. My name is Charla, and I want to welcome you to today's Tech Talk, Distributed Snapshots. Before we begin, we have a couple of housekeeping items to go over. Everyone will have the ability to unmute themselves during the Tech Talk so that you're able to ask questions should you want to. You also have the option of typing in questions in the Q&A panel, should you prefer that. As a courtesy to everyone though, please remain muted when you do not have any questions to avoid any background noise. Also, this Tech Talk session is being recorded and will be sent to everyone via email following the talk. We're also live streaming this talk on YouTube, and the video will be made available there as well. Now that we've taken care of that, I want to thank you all again for joining us for today's Tech Talk. It will be presented by Viliam Durina and moderated by Vladimir Schreiner. Our speaker is Viliam. Viliam is a Jet developer at Hazelcast with previous experience as a full stack developer and architect for enterprise applications and also with computer vision. He's always interested in low-level designs and tries to understand things deeply. He will be joined today by our moderator, Vladimir Schreiner. Vladimir is a technical product manager for Hazelcast with an engineering background, master's degree in computer science, and a deep expertise in stream processing and real-time data pipelines. Vladimir joined Hazelcast in 2016, and he's the product guy behind the Hazelcast Jet streaming engine. With that, I'm going to pass it off to you, Viliam, to get us started with the talk.
Okay, hello everyone. So I was already introduced. I'm Viliam Durina, and this talk is going to be about Chandy-Lamport distributed snapshot algorithm. So I think we can start because we have quite a lot of stuff to do. So what's the agenda for today? So it's two items. The Chandy-Lamport algorithm itself. It's not related to our products. It's just theoretical about the algorithm. As you may know, it's used for snapshotting the state of distributed systems. And then in the second part, I will say how we amended the algorithm in Jet because to fit our needs. So let's start. It will be quite theoretical, but I hope that people will enjoy it. So what is the problem
would you mind me just quickly stepping in? Hi guys, this is Vladimir. One new thing to try for today. We allowed everybody to basically unmute himself or herself and ask the question live. So if you want to either just ask the question in a Q&A as before, or just unmute yourself and ask the question live. Yes. Okay, Vil, okay. Now it's yours.
Yeah, that would be actually welcome if you don't understand or if I'm too quick or something. So what is the problem that the algorithm tries to solve? Distributed system is a system of finite set of processes connected by finite set of channels. And these processes work independently. Each process, they only can communicate over these channels. And we try to snapshot the global state of the system, but it's not possible just by telling them to snapshot, because if we try this, then every process will do it at slightly different moment, and the snapshot will not be consistent. Also, we cannot ask the channels to record messages. We can imagine the channels, for example, as a TCP connection, and the messages can be in some network buffer, in some network router buffer. So it's not possible to snapshot what messages are in transit. We can only record, only the processes can record the messages they receive or they send. Capturing a snapshot of a computation like this is similar to capturing a flying birds that don't fit into one photograph. If you take 3 photographs, the birds moved in the meantime, and when you put these 3 photographs next to each other, it won't be consistent. You will see the same bird in 2 photographs, or if it is flying in the other direction, you will miss some birds. Even if you had 3 cameras and you could somehow very closely snapshot, trigger them, it still will not be exactly consistent. In the real world distributed system, there can be latency, and nothing can be sure that happens at the same instant. We will use this single token system, very simple model of a distributed system, to explain the problem or the algorithm. And using, do you see my cursor when I showing it? Do you see it?
Yes, yes, we are seeing it.
Okay, so using vertices, we model process. This is process P and process Q. And using edges, we model channels. They are always directed. And we name them C and C dash. And this very simple distributed system that is composed of just two processes and two channels, we will use it to explain how this algorithm works. So let's go back. How can we observe the state of this system? If we tell P to record its state, it will do it at one moment. If we tell Q, it may do it a moment later. And in the meantime, some events can happen in the system. So what is the way out of this? How can we observe the state consistently so that it is a state that actually could have happened at some instant in time? Let's go to the algorithm. The algorithm is actually quite simple. This is the entirety of algorithm, but as it is the case with simple algorithms, the devil is in the details. So we will explain it on example next. But first, I will explain the two rules that comprise the algorithm. The first rule is the marker sending rule for process P. This rule says that for each output channel C, a process P sends a marker to C after P records its state and before it sends any other messages along C. So in more simple language, it means that if a process records its state, it must send a marker. Marker is a special message that's inserted in between other messages. So it must send the marker to all its output channels. And the second rule is marker receiving rule. It means that if a process receives a marker, it can happen before or after it already recorded its state. Each process can record state on its own at any time. I will explain later why. So when a process receives a marker, then if it has not yet recorded its state, then it records its state now. It's required to record its state when receiving the marker and records the state of the channel C as empty sequence. Here we see that we are recording the state of channels, but the processes are recording the state of the channels, not the channels themselves. So we record the items that we receive. But when we receive the marker, we record the state of the channel from which we receive the marker as empty sequence. And in the other case, when the process already has recorded the process's state, it records the state of channel C as the sequence of messages received along C after process Q's state was recorded and before Q received the marker along channel C. So again, in simpler words, it means that when a process already recorded its state and receives the marker from another channel, it's sorry, once more. When the process records its state, it starts recording all the messages that it receives along all the channels from which it didn't yet receive the marker. And when it receives the marker from them, it stores it, the sequence. We will show this in example. It may be more clear then. One more note is that the marker sending rule applies each time a process records its state. So not only initially, but each time the process records its state, maybe based on the marker or maybe spontaneously, it is required to send the marker to all its output channels. And any process can record its state spontaneously. That is, that there is no coordination. It's beyond the scope of this paper or of the algorithm. There can be, of course, algorithm. Let's for example, do it at some time, real clock time, but this time is never precise. So essentially, it can do it at any time. This algorithm, to function properly, has a few assumptions. First is that it doesn't handle any failures. So if there is any failure in the distributed system, the algorithm just has to abort. It also assumes that the messages over the channels are delivered exactly once and in first in, first out order. So the channels are reliable. They are just like TCP connections. And it also assumes that there is a route between any two processes. This is to ensure that the marker, when the snapshot is initiated by one of the processes, eventually reaches all of the processes and all of the channels. And these two are the last two I already mentioned. So any process may initiate the snapshot, and each process records its own state and the state of its incoming channels. So let's proceed to an example. I hope it will be more clear after it. So we have this single token system. It has two processes, two channels, and single token. The token is here. We denote it as T, and it can be either in process Q, either in process P, or in one of the channels in transit. And the global state of this process, of this computation, of this distributed system, should tell us where the token was. So let's try to execute, quote quote, this algorithm over this distributed system. Let's say the process P is the one that initiates the snapshot. According to the marker sending rule, it records its state and sends out the markers to all its output channels. Its output channel in this case is just this one, C, and it sends the marker along it. So when process P recorded its state, it recorded empty set because it doesn't own the token. It sent the marker to Q, and Q received the marker sometime later. And based on the marker receiving rule, the second rule, it must record its state now. It owns the token, so it will record a T. So it owns the token. And it must send out the marker to all its outgoing edges. So it will send the it will also record the state of channel C as empty set. This is the second part of the marker receiving rule. And it forwards the marker along the C dash channel. And when process P receives the marker along this C dash channel, it will record the state of the C dash channel again as empty set, because since P recorded its state, no message was received along the C dash channel. And here, as you see, marked with these 4 arrows, these are 4 pieces that together comprise the global state. And as we see, it's consistent because we see the T is there only once, and it's in Q and nowhere else. But one important property of this algorithm is that the system doesn't stop while this algorithm is executed. So it does this snapshotting, we can call it, or this recording of the state in between of all their work that the processes do. Let's have a second example. In this time, the T is in channel C dash. Again, process P decides to initiate the snapshot. It records empty set for itself, sends the marker to Q. Q records this empty set for itself, and records the state of channel C as empty set again. And now P records C dash as containing the item T. And how does it know? Process Q sent the marker after it recorded its state, but since this channel is first in, first out, on the channel is the token, and behind it there is the marker. And eventually the process P receives both these two items, and it must receive the token first and then it receives the marker. And since P started recording when it recorded state, started to record the messages from C dash, it will store, it received the item T during that time, and it will store it as the state of process of channel C dash. And
so
again, we see.
If I may rephrase that, the important property is that the markers actually flow alongside the same connections as the messages, and they can't overtake.
Yes, yes. There are different type of messages sent along the channels. So they are intertwined with the messages, but the order has to be preserved. And what's important to note that it doesn't matter when the process Q sent out the token. It can happen before or after P recorded its state. It doesn't matter. The result will still be the same. We just know from this example that Q emitted token before it received the marker, because otherwise, if Q decided to emit token after it received the marker, it would be in the state of Q, so it would still be consistent. So this example is pretty trivial. Maybe if anyone has any question, I will now proceed to a bit more complex example. So seems okay. Just chime in, and anyone can chime in if you don't understand or if you need to explain something. Maybe I should now mention when the algorithm terminates. It terminates when all channels are recorded. Channels are recorded after processes are recorded. So from this follows that all channels and processes are recorded. How to detect that is also beyond the scope of this paper. But one way can be that actually these processes record their states and the states of the channels to some system, and we know the number of processes and number of channels in that system, and if the number reaches the number of actual processes and channels, the snapshot is complete. But it's beyond the scope of this algorithm. So let's move to a bit more complex example. It's the same distributed system, but in this case we have two tokens, T1, T0, and T1. What's different from the previous example is that in this case, there are multiple possible events that can happen in a system at any time. Let's say we have this initial state. T0 is in P and T1 is in Q. There are two possible events now. Either P can send T0 or Q can send T1. Here in this example, we work with the global state, but this global state only exists in our analysis because it's not possible. This algorithm actually takes the snapshot of the global state, but normally we don't see the global state. But for the sake of this discussion, we know the global state, and we know which event happened first. If it was P sending T0 or Q sending T1. We actually have these two events. First is P sends T0. Now system transitions to this global state. So T0 is in channel C and T1 is still in Q. Now Q sends T1. Now both tokens are in transit. T0 is here, T1 is in C dash. And now P receives T1. So T1 is in P and T0 is in Q. Sorry, in transit. So we have this system, and let's suppose that process P decides to record its state in state S0. What will happen? It owns the T0 token. So it will record my state is T0. It sends marker along C, along the channel, before it sends the T0 event. And now on channel C is the marker, and system goes to states S1, S2, S3, while the marker is still in channel C. What happens now? In S3, let's say, process Q receives the marker. So it records a state of Q as empty, because in the meantime, it sent the item, the token T1 out. And it records the state of channel C as, again, as empty set. And now process Q sends the marker along channel C dash, and P receives it, and it records the state of C dash as T1, because in the meantime it received T1 since the time the process P recorded its state, it received T1 over the C dash channel. And what we see now, the recorded state is it's marked with these tiny arrows. The global state, when we combine it, it's T0 in P and T1 in C dash. But what we can note that it's not any of the intermediate state that the R system went through. How it is possible? How it is possible that we recorded that state that never actually existed in the system? But as I will explain, we can permute the events in the sequence of events to a degree when the events occur in two different processes, because the processes are still parallel. They act independently. So whether P sends T0 first or Q sends T1 first doesn't matter. These two processes are independent. The channels they have are independent. So what we will do, we will mark these events, event 0, event 1, event 2. So event 0 is P sending T0, E1 is Q sending T1, and so on. And we can note that E0 and E1 occur in different processes. So we can reorder them in our fictional analysis. Here is the result. So we see first Q sending T1, which was the event 1. Then we see P sending T0. This was supposed to be E0. There's a mistake. And what we see now, this state S1 with a dash is the one that we have recorded. And there is actually a way an algorithm how to reorder the messages in order to obtain the global state that was recorded. It says that we should move all so-called pre-recording events, that is the events that occurred before the process recorded its state, before all post-recording events. And when we do this, the state after the last pre-recording event is the state that we have recorded. So in this case, Q sending T1, this event 1, occurred before Q recorded its snapshot. So we need to move it before this event. This was supposed to be 0. We move it before it. We interchange these two events, because P sending T0 occurred after P recorded its state, because P recorded T0 as owning it. So it occurred after. And this state, this S1 dash, is the state that we have recorded. If you have a look into the paper, you will find a formal proof that it's maybe a grandfather for mathematicians, but it's quite hard to grasp. I had to read it several times to get it. But they formally prove that there exists a state that was recorded and that is reachable from the state where the snapshot initiated, and from the recorded state, the final state is also reachable. I think I should leave it at this. Maybe you have a gut feeling that how this works. Maybe any questions now?
I don't see any questions, Willow, but to me it sounded quite clear until now. Okay. So let's continue.
That's great. Okay, this is all for the algorithm itself. And now I will present how did we modify the algorithm to adapt it to our needs in JET. So I will very shortly present what Hazelcast JET is. Maybe some people know what is it, but some don't. It's a general purpose distributed stream processing engine. Stream processing means that there are processors and channels, as we see in our distribution system model, and the processor generates some messages and send them over to some other processes, and the next processors receives them and do some other stuff, and this goes on forever. It's stream. The model is directed acyclic graph, and this is an issue. I will explain it in a moment. JET is fault tolerant. We exactly use this distributed snapshot algorithm to take snapshots, and when anything goes wrong, we use it to restart. And one of the distinguishing features of JET is that no special infrastructure is required, of course, besides Java and operating system. You don't need to run any Zookeeper or any database or whatever to run JET. You just run the JET and that's it. It can form cluster. It can you can submit jobs to it, or you can also deploy it as a microservice along with the application. Okay, that's enough about JET. Now I will talk a little bit about the directed acyclic graph and the model, because that's important to understand. So computation in JET is a graph of processors. That's how we call the processes and channels. So this fits to the algorithm. Tick. We have failure detection, so the algorithm doesn't have to care about failures. It runs without failures. If there is a failure, we can tear down the application. It has exactly once and first in, first out channels, so that's also okay. But one more assumption of the algorithm isn't met, and specifically a route between any two processes doesn't exist in JET. JET application is modeled as directed acyclic graph, and specifically this word acyclic prevents that any process is reachable from any other process. But the solution to this problem is simple. We just need to ensure that all source nodes initiate the snapshot, because every other process in the system is reachable from the source. For example, you cannot, if this tokenized process initiated the snapshot, the marker will never reach the source. But if source initiates the snapshot, every other process in the computation will eventually receive the marker. Actually, I can maybe digress a bit. This is a word count computation. So source is reading files, text files, tokenizing, splitting the text files into words, calculates word counts, and sync writes it, let's say, to a file. So it's pretty straightforward. Under the hood, this deck is more complex than what we've seen before. Each of the processors of the stages is parallelized under the hood, and as you see, we have two instances of tokenized processor and two instances of accumulate processors. And the DEG, it's still a DEG, but it got bigger, and it's not the end. JET can run on multiple members. It can run on in a cluster. So we have this same small DEG replicated on every member, and there are channels. With these orange lines, we show that not always it goes to the other member. But what is important, that it's still a DEG. This whole thing that you see here, it's still DEG. By DEG, I mean directly acyclic graph. And besides this, we have a coordinator. There exists only one in each JET job. And this coordinator is used to initiate the snapshot. So it does so at specific times, and it has a channel to all of the sources, and it sends them the marker, and they will start doing the snapshot. You may think that how can we be fault tolerant when there is just one coordinator? But if anything goes wrong, we can just start a new coordinator. Any member can be any member in the cluster can run the coordinator. So it's not a single point of failure. So we actually changed the algorithm that we always ensure that this coordinator starts the snapshot, and it ensures that every single process in the system will eventually receive it and record the state. So this is the first change that we did to the algorithm. So to avoid to work around the limit, to the assumption that every process needs to be reachable, we just know which processor is at the root, and we just initiate the snapshot from there. And the second issue that we changed is that we avoid storing of received messages. This is the state of channels that we called state of channels, is the sequence of messages received along the channel. And how do we do that? This is why do we do that? So the number of items on channel that needs to be stored is unpredictable. There can be a hiccup or maybe GC pause or temporary connectivity issue to some process, and we may be waiting for a very long time to receive marker from that process, and the number of items that we will need to store is unpredictable. It can be few items, it can be millions of items. So that's why we are doing it, and the size of the process state is more predictable. So the size of the channels that we may receive while waiting for the marker is unpredictable, but the state of the processes themselves is like more stable. It generally depends on the number of keys. So for these reasons, we avoid storing of received messages. And how do we do that? The trick is that when a marker is received on a channel, the process stops receiving from that channel. Our processes actually can decide from which channel to take more items. And when we take an item from some channel and see that it is a marker, we stop receiving from that channel and only receive from other channel. And we do it until we have the marker from all other input channels. And only then we record the process state. So it simulates the situation as if the marker was received at the same time along all inputs. Let's have a graphical example. This is our example. This is our processor. It has two inputs, one output, and inputs items on the input X is B. We call it the barrier, but the B is the marker. Barrier or marker, I may use it interchangeably. It's the same thing. So there is a B, and there are two items, two messages, X1, X2. And on channel Y, there is a message Y1, the marker, and Y2. In this order, the order is important. So what happened now, we received the barrier from channel X. So what we will do, that we will stop receiving more items from channel X. We will only process items from channel Y. So here we process the item Y1. This processor just passes on the items it receives, it does nothing with them. So the I1 is already in output. And now we have barriers on or markers on both of the channels. So now is the time when we record the state. Processor records its state and moves on. Now the barrier is in the output, and we can continue processing these items. This approach has a disadvantage. It's not obvious in this example, but I went back 2 screens. This is the initial example. It can happen that these elements on channel Y are not yet there. We will have to wait for them. There may be some more items, but the barrier is not yet there. It can arrive in 10 minutes, let's say, or 10 seconds, let's say. During these 10 seconds, we cannot process these items from X, even though they are readily available to be processed. But we will still be waiting for the barrier from channel Y, which might be blocked temporarily. So these are the disadvantages of this simplification. We see latency hiccup. While waiting for other markers, the processor is partly blocked. For example, garbage collection on one of the nodes will cause other nodes to wait. If one of the nodes is doing garbage collection for, let's say, 2 seconds, and it's supposed to send a barrier, a marker, the other processor will be on other nodes that are not doing garbage collection right now, will be still waiting for the barrier, cannot proceed. And another source of this blocking is, for example, if a source is using blocking IO and doesn't check for messages from coordinator. These barriers act like a synchronization point. They basically stop the process, and the process waits until it has the synchronization message from all its inputs, and only then the process records its state and can proceed. This is the disadvantage, but there is I would say, a partial solution to this, and it's the relaxed at least once guarantee. And if you are fine that some messages are processed multiple times, then you can enable this guarantee, and I will show you in this example what happens under the hood. This is the same example as before. So there is a barrier on channel X. Processor receives it, and what happens now, it doesn't have to wait, it doesn't have to stop processing items from QX, from input X. It can just move on, and when it will receive the marker from all its channels, then it will do the snapshot. So now, as you see, we processed the message A1 from channel Y, and also the messages X1 and X2. There are no more messages on channel X. And now we receive the barrier. So now we will record the state, and we can move on. But the problem with this approach is that the recorded state of the processor, when it records its state, already represents handling of X1 and X2, which originally were before the barrier. And if we restore from this state, like the job fails and restarts, and we restore from this state, what will happen? That we will go back to this state, and the messages processor, and we will restore the processor state, and it already reflects the changes caused by X1 and X2, and X1 and X2 will be delivered again. So they will be essentially processed twice. But in some use cases, this is acceptable, and this removes the delay caused by this synchronization, because there is no synchronization. The processor processes the data as they come and does the snapshot when it has the barrier from all inputs. Sorry. Yes, processor isn't blocked while waiting for markers. So this is the final state. This I already mentioned. JET handles all failures by restarting the job. This includes failures in channels like network connections, or failures in processors like failed node or an exception in the code. And JET executes the snapshot algorithm regularly. So user can configure it, but let's say it configures it every 10 seconds. So every 10 seconds, this algorithm runs, and the state is snapshot. New snapshot, new global consistent snapshot is created. The previous one is deleted. And if the job fails, we will just take the last successful snapshot and restore from it and continue from there. And the snapshot is stored in memory. This is good for if the snapshot is if the state is relatively small, but if you see it in reality, the snapshot is very fast, and it's also very fast to restart should anything go wrong.
Well, actually, let me go a little bit back with one more question. You mentioned that like the general algorithm presented in the beginning suggests recording the state of a whole channel. But what you did was the simplification in order to avoid recording the state of the channel.
Yes.
And as a trade-off, you get a simplified version of the algorithm, but with a possible issue of those basically latency issues. Sometimes you have to wait for markers from all input edges. Would that be, why is it impractical to basically store the content of the channel? Is that even doable, or why did you decide not to?
It is doable, but it's unpredictable. That's the issue. You don't know the size of the state. If you are processing many items and for some reason you need to wait for a long time, you might be needing to store a lot more data than you for one snapshot than you do for the other snapshot. That's the only reason. We could implement it, but this is the only reason.
I see.
As far as I know.
And even if the size of this channel is somehow kept,
you cannot keep it, because
gap. I mean, there is it's a queue with a fixed size, for example. So we introduce more.
Yes, the queue has fixed size or limited size, but it doesn't mean that in the queue there is the marker. You have queue of, let's say, 1,000 items. You process them, and there are another 1,000 items, and there can be million items, and only then you can get the marker. So we don't know. It doesn't matter that the queue is fixed size. It's like when you open the door and let the people in who are waiting at the door. So there is limited space behind the door. But if you do it many times, you will have unlimited number of people letting in, as an analogy. And you cannot avoid this, because when you store or when you record the state of the process, you must record all messages received along the channels until you receive the marker from that channel. So what we did, we postponed the recording of the processor state until the moment that we receive the marker from all inputs. So we record the state later, but this prevents us from processing any items that are behind the markers.
Got it. That makes sense. Thank you.
Okay, any other questions? Maybe how many? We have 10 participants, not too many people. Did you other people get the idea of the algorithm, or do you understand how it works?
Now everybody's shy confirming that they get it.
Maybe you will have to watch it once more, but I spent quite some time understanding it. Actually, we implemented it in Jet like 2 years ago. I had to read the paper when preparing for this talk like 2 or 3 times.
Will, another question from me to give attendees more time. So it's clear that this approach, including the simplification that you described, is really applicable for the data flow based tools. So the tools that are basically designed as a set of processes that form a graph that's directed and acyclic and communicate this way. Do you know about any other use case of this approach in the distributed systems?
Different use case? I don't know. It's.
I'm wondering whether, whether, for example, like actor systems such as Akka follow this, or maybe not, because in Akka you can have cycles. The messages
cycles don't matter. Cycles don't matter to the algorithm. We don't have them in Jet. That's why we had to do these changes, but they don't matter. The algorithm works. Each process, if the process receives the marker multiple times, it will actually receive it once from each channel, but it will only record its state once. So all processes will record their state only once, and the propagation will stop even there is a cycle. There is this marker receiver rule that says that you stop when you you record your state only when you receive the first marker. The next marker, you only record the state of the channels you receive them from, and you will receive it once from each channel. So it will stop deterministically. In the paper, there is also a proof that the algorithm eventually terminates. It's quite formal. I like it. I liked it.
Mm-hmm. All right.
But you can model any distributed computation like this. I don't know, any system that has parallel processes can communicate like this. Even if you are just doing multi-threaded programming, you have each thread is a process, and they communicate. If they communicate using channels, the channel can be just a variable that you set. It can be abstracted as a single element channel that you can implement this algorithm in this and get the global consistent state of your system.
Vilo, thank you. We are getting no more questions. I saw that the next slide was QA/thank you slide. Is there anything else you would like to add?
I don't know. Not.
All right. Well, thank you very much. I mean, I really appreciate such a low-level topic. It's a 5th talk, I guess, in this series, and we had like a basics talk about caching. There were the use case focus talks about CDC and this machine learning thing. And this was like first really low-level talk in the series, and I think it was great. So thank you very much. And to announce the next agenda, next talk will be actually in 2 weeks. So we are relaxing the schedule for bi-weekly talks. And we're going to host Hussein Balal, who has a unique experience of building a fully managed cloud service. So what he did is that he has taken basically on-premise middleware, like library, and made it a managed service. And what he did was using Kubernetes to build a control plane for the solution. He was playing a lot with like fault tolerance and the trade-offs involved. He spent quite a lot of time fine-tuning the DevOps practices. So I think it's going to be also, again, another kind of view and very interesting talks. So again, in 2 weeks, just follow your usual channels, and the talk will be announced there. Thank you very much for attending, and have a nice day. Goodbye.
Bye-bye.